Welcome to the enigmatic realm of antimatter, a substance that exists in the shadows of our universe, challenging our very understanding of reality. Antimatter is not just a whimsical notion from science fiction. It is a genuine phenomenon that has captivated scientists, philosophers, and dreamers alike for decades. But what is antimatter? And what transformative possibilities would arise if we discovered it in significant quantities? Join us as we embark on an enlightening journey into the mysteries of antimatter, exploring its properties, implications, and the groundbreaking discoveries that lie ahead on the horizon of science. To fully comprehend the concept of antimatter, we first need to grasp the fundamental nature of matter itself. Matter is the substance that constitutes everything around us, from the stars in the sky to the very air we breathe. It is composed of atoms, which are made up of protons, neutrons, and electrons. Antimatter, however, is like a cosmic mirror image of matter. For every particle that exists, there is an antiparticle that possesses the same mass but an opposite charge. For example, the antiparticle of an electron is known as a positron, which carries a positive charge rather than a negative one. Similarly, protons have antiprotons and neutrons have antineutrons. This fundamental symmetry is not just a curiosity. It reveals deeper insights into the nature of the universe. When a particle encounters its antiparticle, the two annihilate each other, releasing a tremendous amount of energy in the form of gamma rays, a process that has fascinated physicists and sparked countless questions about the nature of reality. This annihilation is described by Einstein's iconic equation, E equals mc squared, illustrating the staggering energy locked within even the tiniest amounts of mass. It's this energy release that fuels speculation about potential applications of antimatter and why scientists are so eager to study it further. The journey to discover antimatter began in the early 20th century, a time marked by extraordinary advancements in physics and an insatiable curiosity about the universe. In 1928, British physicist Paul Dirac made a groundbreaking proposal by merging quantum mechanics with the principles of special relativity. His revolutionary equations hinted at the existence of particles that had yet to be observed, thus laying the foundation for the concept of antimatter. The first actual confirmation of antimatter came in 1932 when American physicist Carl Anderson made a remarkable discovery. While studying cosmic rays, he detected positrons, clear evidence of antimatter that not only validated Dirac's theories but also marked a monumental moment in the field of particle physics. Anderson's work earned him a Nobel Prize and opened the door to further exploration of the universe's fundamental components. Following this discovery, physicists around the world began to experiment with creating antimatter. Advancements in particle accelerators allowed researchers to produce small amounts of antimatter, with facilities like CERN in Switzerland successfully creating antihydrogen, an antimatter atom formed from a positron and an antiproton. However, the quantities produced are minuscule, often measured in billionths of a gram, highlighting the challenges that lie ahead in understanding and utilizing this elusive substance. Storing antimatter presents a significant challenge for researchers. Since antimatter annihilates upon contact with ordinary matter, scientists must devise intricate methods to isolate it. Advanced technologies, such as magnetic traps and vacuum chambers, are employed to prevent any interaction with matter. Imagine a high-tech magnetic bottle designed to hold antimatter in a vacuum where every particle is carefully suspended in a controlled environment. The technology involves using powerful magnetic fields to keep antimatter away from the walls of its container. Any breach could lead to a catastrophic annihilation event, releasing energy in a violent burst. Despite these innovations, the task of producing and retaining enough antimatter for practical applications remains a formidable obstacle. Currently, the amount of antimatter that can be created is minuscule, often just a few atoms at a time. The cost of production is astronomical, estimated at billions of dollars per gram. This raises crucial questions about the feasibility of using antimatter in practical applications, even as researchers strive to understand its fundamental properties. But what if we found substantial amounts of antimatter? The implications would be nothing short of revolutionary. One of the most thrilling prospects is its potential for energy production. Antimatter possesses the highest energy density of any known substance. Just 1 gram of antimatter could yield energy equivalent to the explosive power of several tons of conventional explosives. This raises exciting possibilities for energy generation, potentially providing clean, abundant power for cities, vehicles, and beyond. Imagine harnessing this energy for electricity generation on a scale we have never seen before, powering our world in ways that could minimize our reliance on fossil fuels and mitigate climate change. This could reshape our approach to energy consumption, leading to a sustainable future. Moreover, antimatter could dramatically transform space travel. Picture spacecraft equipped with antimatter engines capable of propelling us across vast cosmic distances at speeds that would bring distant stars within reach. Such technology could pave the way for interstellar exploration, allowing humanity to venture into realms once thought unreachable. If we could utilize antimatter propulsion, journeys that currently take years could potentially be accomplished in months, unlocking the mysteries of our solar system and beyond. Antimatter also holds the key to some of the most profound questions in cosmology. The observable universe is predominantly composed of matter, which leads us to the so-called matter-antimatter asymmetry problem. If matter and antimatter were created in equal amounts during the Big Bang, why do we observe such a preponderance of matter today? Understanding antimatter could illuminate this mystery, providing insights into the fundamental laws that govern our universe. Ongoing experiments at facilities like CERN are dedicated to this investigation, as scientists strive to uncover why our universe appears to favor matter over antimatter. By studying the properties and behaviors of antimatter, researchers hope to unravel the underlying principles that dictate the very existence of our cosmos. This inquiry not only seeks to explain the imbalance of matter and antimatter, but could also lead to new physics beyond the standard model. It's a quest that challenges our understanding of everything from the origins of the universe to the fundamental forces that shape it. In conclusion, the mysteries of antimatter represent a tantalizing frontier in our understanding of the universe. While we've made significant strides in exploring this elusive substance, the journey is just beginning. The potential discoveries, both in technology and in our understanding of the cosmos, are immense. As we continue to unravel the mysteries of antimatter, we edge closer to answering fundamental questions about existence and our place in the universe. Thank you for joining us on this captivating journey into the world of antimatter. If you found this exploration intriguing, be sure to like, subscribe, and stay tuned for more enthralling stories from the universe around us. Together, let's continue to unveil the wonders of our cosmic home, one groundbreaking discovery at a time.